Hello everyone. So today we are going to discuss the atomic structure, specifically focusing on particles in the atoms and atomic radius, and also isotopes. At the end, I'll also look at some style questions. You can download this worksheet on the screen using the link down below. So we're going to talk about the basic structure of an atom, definition of terms, and distribution of mass and charge within an atom, and then behavior of these particles within an electric field. And also, I'm gonna talk about the radius, ionic and atomic radius, and isotopes as well. At the end, we're gonna look at exam style questions of particles in atoms and isotopes exam style questions. So let's begin straight away by defining with explaining what an atom is, its structure, what it comprises of, the subatomic elements of an atom. So these are just notes that you can refer to back when you forgot something. So I've compiled these notes from different sources, and I believe everything on it is true. So the smallest part of an element is an atom. Suppose, let's say, for example, the zinc element is made up of its atoms, and then the atom are mostly empty space surrounding a very small dense nucleus. So here, this is the diagram of an atom, right? We have uh, on this diagram. Uh, on this diagram, I have this nucleus, the inside thing, the dense part of an atom is called a nucleus, and then outside that nucleus, we have the shells where electrons are, and then the nucleus, like the dense part of an atom, contains protons and neutrons, and then the nucleus has an overall positive charge because of positively charged protons. And then we can also see that the neutrons have no charge and they are neutral. They have no charge. They are neither positive or negative. And then outside the nucleus, we have these shells where electrons are, and then electrons are negatively charged and are found in shells in an empty space around the nucleus. So around the nucleus of an atom is empty space, right? So this empty space, that's where we find electrons that are um, negatively charged. So subatomic particles of an atom are electrons, protons, and neutrons. So below is a table about relative charges and relative masses of subatomic particles. So from the table you can see that the proton, right, is positively, the relative charge of the proton is +1, and then the relative mass of is 1, and then its location within an atom is the nucleus. Then the neutron, the relative charge is 0, it is no charge, it's not positive or negative, and then the relative mass is 1, and then its location is in the nucleus. So in the nucleus we have protons plus neutrons. Then outside, on the outer space of the nucleus, like on the outer space of the atom, like outside, like surrounding the nucleus, that's where we have the electrons. Here I have electrons. So if you look at my diagram, you can visualize clearly. Then finally the electron, the relative charge is -1, and then the relative mass is 1/1836, and then its location is shells in empty space around the nucleus. So I want to explain why I wrote it as relative charge, relative mass, because the protons and the electrons are so small. They are so small that we can't measure its mass to say the mass of a proton is 1 times 10, this number times 10 to the power minus very big number. It won't make sense to have such a small number. So for scientists decided to measure the mass relative to each other, we can't actually measure the mass. So when you say the mass of a proton is 1, right, we mean because they measure the proton, the neutron, and the electron, and they saw that the protons and the neutrons are a higher mass than the electrons, because the mass of a proton, right? Mass of a proton equals to mass of a neutron. They have equal masses, so they thus refer that as one. To say the mass of a proton, let's refer to it to as 1 unit. But the mass of an electron was 1,836 times smaller than the mass of both the proton and the neutron. That's why we say it's 1 over 1836. So usually in your textbooks you find that it is said that the mass of an electron is negligible. It doesn't contribute to the total mass of an atom because it's so small. It's 1 over 1836, smaller than the mass of um, it's 1836, smaller than the mass of proton and neutron. So these masses, these are not actual masses, they are just relative masses, so that we can be able to to make our calculations and um, do our stuff. So if you are these bullet points are explaining the same thing, that we can measure the actual mass because they are so small. Instead, we do the relative, we compare them to each other to say compared to the mass. Let's say measuring the mass of electron, we say comparing this mass of electron to the mass of protons and neutrons. How much smaller is it? It was found to be 1836 times smaller. And then that's why we have these relative masses. Then scroll, we go down to the definition of terms, right? So you need to know sometimes a little bit of terms for you to be able to answer the Cambridge questions about atoms and atomic structure. So firstly, we would define the atomic number. Atomic number is also equals to proton number. We can say atomic number or proton number, which is the number of protons in the nucleus of an atom, right? So the number of protons is called atomic number or proton number. And also atomic number is equal to the number of electrons present in the atom that has a net charge of 0. Please take note, if we have an atom with a net charge of 0, it means that the atomic number is equal to the number of electrons. But we have to make some adjustments if that atom is something like the charge of that atom is not 0. So we need to make some adjustments. For example, the atomic number of neutron magnesium is 12. So if the magnesium is 12, yes, atomic number 12, which means the number of electrons is 12 as well. But let's say we have magnesium 2 plus, then the proton number will still be 12, because for us to get 12 plus, we have to lose 2 electrons, but the number of electrons won't be 12. We need to make adjustments. Let's say to say how many electrons have we lost? We lost 2 electrons, so we need to say 12 minus 2 to make them 10 electrons left. So it should be neutral, a neutral atom with the same number of protons and electrons. So you find these type of questions in your paper ones, like in your Cambridge paper ones, and then it got to define the mass number or nuclear number. So the mass number is equals to is the total number of protons and neutrons. Since the nucleus is the thing that contributes to the mass, it's the only thing, it's the only component in an atom that contributes to its mass, because it's the total number of protons and neutrons in the nucleus of an atom. And then so I've wrote this formula in bold, say mass number equals to protons plus neutrons. So yeah, mass number equals to number of protons plus neutrons, and then the number of neutrons goes to mass number minus atomic number, or nuclear number minus proton number, something like that. Both ways. So mass number, say, is also called nuclear number, and then atomic number is also called proton number. So nuclear number is equals to mass number. So it just an other number. So nucleons refer to protons and neutrons because they are found in the nucleus. So you need to understand this structure where A symbolizes the chemical symbol, and then X mass of an mass or nuclear number, and then Y represents this Y below here. It will be the smallest number, represent the atomic number, also called the proton number. And then X represents the mass number, also called the the mass number, uh, also called the nuclear number. So, uh, so let's give it an example to say magnesium, right? It's a magnesium 24 and 12. It means 12 is equals to what? Uh, 12 is equals to the atomic number or proton number, but 24 is equals to the mass number, and then this is the chemical symbol Mg for magnesium, and then this is a neutral. It is no charge, but it is, if it is 2 plus, it means the proton number will still be 12, but the electron number will be different. It will be something else. Then we go down to the distribution of mass and charge within an atom. So the nucleus contains the heaviest subatomic particles, which is the proton and neutrons, which means the mass of an atom is concentrated in the nucleus. The mass of electrons doesn't contribute to the mass of an atom. It doesn't contribute to the mass of an atom. That's supposed to be atom. Since the mass of electrons is negligible, the nucleus is positively charged due to the protons, and then is negligible electrons orbit around the nucleus. It creates a cloud of negative charge, right? So when we go back to our structure, this is our nucleus, and then these are electrons orbiting around the nucleus. So as they orbit around the nucleus, it creates a cloud of negative charges created. Right? A cloud of negative charges created. So the electrostatic attraction between the positive nucleus and negatively charged electrons orbiting it holds the atom together. So for the atom to be together, it is the two forces, the the positive and the negative charges attracting each other, that holds the atom together. And then if we for interest sake, let's say this is our want to see the behavior of protons, of neutrons, and of electrons in an electric field. So this is a positively charged plate, and then this is a negatively charged plate. So if we shoot a beam, right, beam of particles at the same velocity, they should be at the same speed. We will see that neutrons are not deflected in the field because they have no charge. They are neither positively charged or negatively charged. They have no charge. The charge of neutrons is zero, so it's not deflected. It passes through straight. And then for electrons in red, they are pulled towards positive plate. It's an evidence that electrons are negatively charged. And then if you compare them, right? If you compare them, the protons, they are supposed to be here, right? Protons are supposed to be here. Why? Because protons are heavier, so they cannot take time to be pulled to the negative plate. They are pulled to the negative plate because they are positively charged, but they are taking time to be pulled because they are heavier. But electrons, they are negligible and negative, so they are pulled fast to the positive plate. So the plate points here explain the same things that I've explained earlier. So next thing I'm going to look at is the atomic radius. Yeah. So atomic radius of an element is a measure of size of an atom, and it is found by dividing the distance between the centers of two nuclei by 2. The nuclei should be covalently bonded. So suppose this is a hydrogen atom. So let's make it. This is the oxygen, right? So oxygen molecule, the oxygen molecule is covalently bonded. So what we need to do is measure this distance and then divide it by 2. That's how we find the atomic radius of an atom. So the atomic radius, like for elements on the periodic table, it decreases across the period, and then it increases down the group. So we explain why it decreases using the electron shell theory. So when using the electron shell theory, we can explain why it decreases across the period. For those that might not understand what a period is, so going across here, that's what we call a period, and then going down here, that's a group. So atomic radius decreases as you move across a period, because across the period there is increase in number of protons, hence increased nuclear charge. But at the same time, extra electrons are added to the same principle of quantum shell. The larger the nuclear charge, right? If we increase the nuclear charge, nuclear charge is positive, the greater the pull of the nuclear on the electrons, which is resulting in smaller atoms. So if you see here, say it decreases across the period, right? An element here, if we have an element here, is atoms with greater number of, so this is usually helium, this is hydrogen, right? This is usually helium, this is hydrogen. So the, the radius of hydrogen is greater than the radius of helium, because why? Because hydrogen is one proton, right? And then helium is two protons. So across the period, we increase the number of protons. So in this case, it's from one proton to two protons, right? So the increased number of protons means that there is increased nuclear charge. Helium has increased the number of nuclear charge, although we have increased number of electrons across, but it's still in the same principal quantum shell. There's no increase in the number of shells. So that greater nuclear charge will pull the electrons in the same number of in the same principal quantum shell closer, making making the radius of the atom shorter. So we'll see that it's due to the increase in the, so across decreasing across the period is increasing positive nuclear charge. So the increased positive nuclear charge will pull the electrons closer, making the atomic radius smaller. And then it increases down the group, right? So we will see that here the radius of an atom here compared to the radius of atom here, this one is bigger, this one is smaller, because we have increased the number of shells, the number of principal quantum shells, therefore making the atomic radius greater. So that's how we use the electron shell theory to explain why it decreases across the period, increasing down the group. So same applies to so we can see here that see that this hydrogen is smaller than this helium, because we have one proton here, we have two protons. So this is greater nuclear charge, right? Which means greater attraction, so small proton. And then we have this cesium has greater number of shells compared to hydrogen, so it's bigger, so increasing atomic radius from this diagram. And then same applies to ionic radius. We use the electron shell theory to say so for ionic radius, it increases with increasing negative charge. So if negative charge increases, right, the ionic radius also increases. So why is that happen? So if you see it fluorine here, right, we have fluorine here, we have fluorine, right, and then we have oxygen. So this is F minus and then O2 minus. So O2 minus is 73 picometers, and then this one is 71 picometers. So as we, with increasing negative charges, the ionic radius increases. Why? Because let's say to get O2 minus, we're adding two electrons, but to get F minus, we are just adding one electron. We are adding one electron. So so negatively charged ions are found by an atom accepting electrons, while the nuclear charge remains the same. The outermost electrons are further away from the positively charged nucleus and are therefore held only weakly to the nucleus, hence greater ionic radius. And then we can see that if we increase the positive, like if we increase the positive charge, I say this is 3 plus, 2 plus, this is 1 plus. With increasing positive charge, we have decreased ionic radius. The ionic radius decreases as the positive charge increases. So positively charged ions are formed by atoms losing electrons. The nuclear charge remains the same, but there are now fewer electrons than they were, which are under electrostatic force of attraction to the nucleus, which decrease the ionic radius. So the greater the positive charge, right, the smaller the ionic radius. Then the next thing I'm going to talk about are the isotopes. So isotopes are atoms of the same element that contain the same number of protons and electrons but different number of neutrons. So here I've put an example of isotopes of what? Of hydrogen, right? So for example, let's another example is carbon. Carbon 12 and carbon 14 are isotopes of carbon. They contain 6 and 8 neutrons respectively, but carbon 12 is the same number of protons and neutrons, and then carbon 14 again is the same number of protons and electrons, and then here is same number of protons and electrons. But what's different is the number of neutrons. So that's why you have for this one you have 6 neutrons, and then for that one you have 8 neutrons. But the number of protons and electrons are the same for isotope. I've included several examples for the isotopes of hydrogen. So we know that here the proton number remains the same. Same applies to electron number. So the proton number and this electron number are the same, right? And then what changes is the number of neutrons. So for protium, it's 0 neutrons. For deuterium, it's 1. For deuterium, is 1 neutron, and then for tritium, right? For tritium, it's 2 neutrons. So in isotopes, what's different is the number of neutrons, not the number of neutrons, not the number of protons or electrons. So isotopes have similar chemical properties but different physical properties. So for chemical properties, right, so since we say for every isotopes, number of protons are the same and number of what? Electrons. So from our diagram, it was like this, right? This is our nucleus where protons are. These are what? Electrons, 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 electrons. So for chemical properties, these electrons are involved in a chemical reaction. So because they are involved in a chemical reaction, there is the same number for each and every isotope. Let's say carbon 12, right, and carbon 14. These have similar chemical properties because they have the same number of what? Of electrons which are involved in a chemical reaction. But the physical properties are different because this one, carbon 14, has 2 more neutrons than this, of which neutrons there's a unit mass, relative unit mass, like relative unit mass of 1, right? Which means it will affect the mass. The mass of carbon 14 will be different from the mass of carbon 12. That's why we say physical properties are what? Are different, but chemical properties of our isotopes are the same. So if you read carefully these 2 points, they actually explain what I was saying. And then if you are doing Cambridge, you use this periodic table and some important data values. I just included them so that they're convenient, you can find them for questions. So we are done with the explaining part, and then let's dive into the most interesting part, which are the questions, right? So for these questions, what I do is I take them strictly from Cambridge exam, like from Cambridge website. I will promise to work only with Cambridge questions to demonstrate what I will be explaining in that video. So you realize that there are some questions that I haven't discussed. So about electronic configuration. So I would like you to check my next video. I'll be explaining about the electronic configuration of certain elements, right? So what I do is I for every worksheet I include where I took the question. So this is 9701, that's the syllabus code. This is 21, that's paper, let's say paper 2, variant 1, and then this is May, June, and then this is 2022. That's the so for every question I've done that. So 97, like for this one, and then again for this one where I took the question. So for other people who would want to refer and then maybe look at the exam report, you can just look at the bottom right. So let's get into the question, right? The first question is, so I'll update the numbers. So I have written 1. So for you not to be confused, I will include the numbers of exactly the question paper, so I got the questions. So this is 1G part 1, right? So it says this thing, is an isotope of magnesium, right? Determine the number of protons and neutrons in an atom of G of this one. So number of protons, what are the number of protons? So from our notes, it was from here, I've talked about so it was X, which is the mass number or nucleon number, and then Y, which is the proton number. So you should know this whole thing, and then A is the chemical symbol. So we're gonna use the same thing again. So we're gonna say so here it's agreed. This is the what mass number, which is also nucleon number, and then this one is proton number, which is equals to electron number. So proton number or atom number. So number of protons are already there. That's the smallest value for this symbol, which is what 12. And then the number of neutrons, right? The number of neutrons, we said the number of neutrons equals to of neutrons, right? Equals to mass number minus proton number. So in this case, what's the mass number? Mass number is 25, right? Minus 12, which gives us what? 13. So this gives us 13, right? And then, so that's all you need. That's all you need. And then if you go to D part 2, it says state the full electronic configuration of an atom of this one, right? Of that isotope. So I said earlier, like uh, um, I even explained how we do the full electronic configuration, but this is easy as long as you have your periodic table. This is easy. So it says full electronic configuration of an atom of what? Magnesium. So we want to get to magnesium. So what I want you to do is, here's the different explanation on how to get the configuration. But I just wanna quick introduction. So this is hydrogen, this is helium. So let's rub out this and then rub out this. So what I want you to do is, we need, for electronic configuration, we need to move certain steps from hydrogen to that element. That's how we get the electronic configuration. So this is called an S block. The whole of this one is an S block, right? And then this one is called a D block. This one is a D block, and then this one is called the P block. So this is period number 1, period number 2, period number 3, period number 4, period number 5, period number 6, period number 7. And then here you number from 3, 4, 5, 6, going down. So you need this, like you need this if you want to get it right, like not to get it wrong. So we need to get what? To magnesium from hydrogen. That's how we get the electronic configuration. So we are in which period? So from we are, this is our start point, right? This is our start point, this is our end point. So from hydrogen, right? Which we are we in which period? We are in period 1, and then which block is that? It's S block. So we move how many steps? It's 1, 2 steps. So it's 1 is 2, and then there's nothing here since I said we should we considered hydrogen and helium already. And then we go on to the next period, which is period what? Period 2. We write our 2. And then we are in which block? We are in S block, right? And then how many steps do we need? It's 1, 2. So it's 2s2. So it's 1s2, 2s2 so far. We haven't reached to magnesium yet, and then we go again, right? After we reach the P block, right? But in within the same period, which is period 2, which block are we in? We are in P block. So how many steps do we need? Is 1, 2, 3, 4, 5, 6. So we include 6. So 1s2, 2s2, 2p6, right? And then we haven't reached magnesium yet, so we go again to the next period, which is period 3. How many, which block are we in? It's S block. And then how many steps do we need? It's 1, 2. So it's 1s2, 2s2, 2p6, 3s2. So you need to see that this one is the period that we are in. This one, uh, this one is the block is either S block, D block, or P block, right? And this one, these are the number of steps. Let's say 2 steps, 6 steps, something like that, until you reach the element that you want. So it will be 1s2, 2s2, 2p6, 3s2. So if we go down, we can write our answers. 1s2, right? 2s2, 2p6, 3s2. That's the electronic configuration of what? Of the atom of magnesium, right? And then for this one, define, it says a symbol of magnesium contains 3 isotopes, 1, 2, and that isotope, right? The percentage abundance of 3 isotopes is shown in table 1.1. So isotope of magnesium, is this one. So these are the isotopes of magnesium, and then these are the respective masses and then respective abundances. So it says the relative atomic mass AR is calculated by comparing the average mass of the isotopes of an element of the unified atomic mass. Define the unified atomic mass. So scientists agreed to use carbon, like I don't know, as a symbol. Yeah. So when you're defining the unified atomic mass, it should be, since carbon is mass 12, carbon 12, yeah, that's they agreed on carbon 12. So you just say 1 over 12 of the mass of, so it's 1 over 12 of the mass of carbon 12. And then the next question is calculate the mass of X, and then it says calculate this mass at use data from table 1.1 and AR from AR is magnesium. We are given that the relative atomic mass is 24.31. In your calculation, sure working. So I want you to take down this formula to say AR equals to mass times respective percentage abundance of each and every of isotope 1, mass times percentage abundance of isotope 2, going downwards, and then over 100. So that's the formula we are going to use. And then if I substitute, right? We're given AR is 24.31, right? 24.31 equals to mass times percentage abundance. Let's call this mass X. So we're going to multiply, that's mass times percentage abundance. So which is equals to 78.99 times X, right? That's the first isotope. And then the next isotope is 24.99 times 10.00. And then the next isotope is plus so it's 25.98 times 11.01, right? Or over what? 100. So we need to solve for X, and then you need to rearrange. So if you rearrange, it will be X equals to 24.31 minus a couple of I don't have my calculator now, so I'm going to say 24.99 times 10 plus 25.98 times 11.01 square bracket O over what? O over 78.99. So if you punch this in your calculator, you will find the mass of X. So you need to use the formula to say AR equals to mass times percentage abundance plus of one isotope and then the next isotope and that of 100, then rearrange, then you'll find your answer. Then says the part 3 says state one similarity and one difference in the properties of these isotopes of magnesium. So as I said earlier, right, similarities of isotopes and then differences of isotopes. So similarities of isotopes are the chemical properties, right? Chemical properties and proton number. If the proton number is similar, which means the number of electrons is the same, of which the number of electrons they affect the configuration of that the affect the configuration of that atom. So we say the chemical properties and the proton number, which means the electronic configuration is also the same, and then the differences are the physical properties, and also the physical properties are different, and also the number of what neutrons are different. So I think that's that's the simple question of atomic structure, like on isotopes and stuff like that. And then in my next video, I'm going to explain how we can fully about the electronic configuration, right? And then if you have any questions, let me know in the comments. And then I would want you to do question 1E, and then if you do again question 1. So I've left 2 questions for you guys just to try on, and then if you want me to do them, to make a video doing them, you can let me again in the comments. So guys, thank you for watching, and then subscribe for more chemistry. For more chemistry lessons, I'm going to do like the whole chemistry A syllabus. And then if I see that you like my videos, guys, I'm also going to do the A2 chemistry. So if you need any subject, let's say you need to make videos on computer science, on maths, further maths, I did all those subjects on physics, just let me know again in the comments. And then please like my video. If you like my video, please like it. If you don't like it, please just leave it. If you please subscribe for more videos, because I'm gonna be dropping more videos on chemistry AS. Thank you guys, and I'll see you next time.